Hello. So in this video we're going to be talking about how to solve equalities and inequalities that have absolute values in them. Okay, so to do this we're actually going to sort of just go through a problem and develop a method as we go. So suppose we have this problem, right? Find all x and r, right? So this is x element of real numbers, so find all the real number x's such that this inequality holds, right? So I have the absolute value of 3x plus 1. That quantity minus 2 has to be strictly less than 2x. All right. So as I've sort of mentioned before, absolute values are great from a geometric perspective, right? They're very sort of intuitive when you think about them as distances. Unfortunately, if I'm going to answer an analytic question, right, something with algebra like this, it's very hard to do that generally with some geometric argument. So typically what we need to do then is use the analytic argument, meaning that we need to do that, or at least sort of something similar to that whole piecewise definition of absolute value that we talked about in the analytics section. So in particular, what I need to do is figure out when this absolute value does nothing, right, versus when it has to flip a sign. And if you remember from the analytic part, what I'm really saying there when I say that is I need to know when the inside is non-negative, right, is strictly greater than 0 or 0. So first thing I'm going to do is take all of what's inside the absolute value. So whatever's in the absolute value, copy that down, so 3x plus 1 in this case. And I want to set this greater than or equal to 0 and find what x's make that true. So if I subtract the 1 over, divide by 3, I'm going to have x greater than or equal to negative 1/3. Okay? So what this is saying then is if x is greater than or equal to negative 1/3, the inside is positive. And you remember, if the inside is positive, then the absolute values do nothing. So what I need to do next is take this starting equation, this thing I have here, and break it into two cases. And so you sort of want to literally do exactly that. So I'm going to break this down into some case 1. So I'll write it sort of next to it over here. So case 1 is going to be exactly when this is true. So when x is greater than or equal to negative 1/3. And then when that's true, the absolute value, right, because the inside is 0 or higher, so that means that the absolute value is doing nothing. So I can replace it with just parentheses. So I'm going to have 3x plus 1 in parentheses, and then the rest. So minus 2 less than 2x. So that's case 1. At the same time, I don't have to do them at the same time, but just to emphasize, I'm going to have another case, case 2. And case 2 is the what we would call the complement, all the other times. So here, when x is greater than or equal to negative 1/3, right? So for people that are better at visualizing things, this case, in fact, I'll do it in blue so it matches, right? If I have 0 here, negative 1 here, so negative 1/3 is like there. So I have this, right, everything to the right of that negative 1/3. But that means that the complement is everything else. So it's everything strictly left of negative 1/3. So case 2 is going to be the complement, less than negative 1/3. Probably got my colors backwards, but hopefully you guys can follow along okay. And in that case, when I'm to the left, right, specifically when I'm in the situation where the inside is not positive, the inside being negative then, so in the case where the inside of the absolute value is negative, that means the absolute value flips the sign. We talked about that in the analytic video. If you don't remember, go check that again. But that means that I'm going to replace the absolute value with parentheses, but put a negative in front. So I have negative 3x plus 1 minus 2 less than 2x. So I have two cases here. So I don't have to like solve them in tandem. I don't have to do like one and the other at the same time. So I'm just going to do this one down and solve it, and then I'm going to do that one and solve it, and then we'll talk about it at that point. So once I've gotten these broken into cases, you just solve it like you would a normal inequality. So here I have 3x plus 1 minus 2, so I have 3x minus 1 less than 2x. So I can subtract 2x over and add 1 over. So if I subtract 2x over, I'm going to have just x left, right, because I have 3x minus 2x. Adding 1 over, I'm just going to have x less than 1, okay? Same idea over here. So I'm going to have negative 3x minus 1 minus 2, so I'm going to have minus 3 less than 2x. So then I can add the 3x over. So I'm going to have negative 3 less than 5x, right? And then divide by 5, excuse me. So I'm going to have negative 3/5 strictly less than x. Okay. So I've solved, right? But here's the thing. I haven't finished yet, and there's a very easy to forget step here. So I really want to sort of draw attention to it. So what I'm going to do is draw out the same sort of solution thing I did here, because they work really well with inequalities. So here I'm going to have, again, something like this. I want x less than 1, so I guess let's put 0 in the middle. Let's put 1 here, 2, 3, negative 1, negative 3, negative 2. Okay. So my solution appears to be x is strictly less than 1. So strictly less, right, I want the open bubble. So I'm going to graph this sort of just above. And just so it's clear, this is really x less than 1. You don't have to write it on there, I'm just saying that's what that line is for. But I'm making that clear because the thing that's easy to forget is that this is a solution under this assumption, right? The only reason why we can just replace the absolute value with parentheses is if we know for a fact x is greater than or equal to negative 1/3. So the extra step that you need to do is to also graph the assumption. So I want to graph x greater than or equal, so it's a closed dot, negative 1/3. So negative 1/3 is sort of around here-ish, give or take. So I have a closed dot at negative 1/3, and it's greater than or equal, so it's this direction. And the final, for this case, the final solution then is where this and that are both true, meaning where they overlap, okay? So they overlap starting at negative 1/3 and going up to 1. It doesn't include 1 because of the open dot, right, the open circle right there. But it does have the closed circle over here, so it does include negative 1/3. Okay? So this then is the solution for case 1, because I got this from the actual algebra, but I also have to account for this assumption. That's why I need both of these. And so I'm going to do the same thing here, okay? So again, I'm going to graph. Guess I don't need as many numbers, so let me do like, let's do, sorry, that should have been 0, 1, 2, negative 1, negative 2, and this is a terrible 0. Let me fix that in case somebody pauses the video and thinks they're looking at some sort of fee or something. There we go. Okay. So again, same sort of approach. I'm going to start by doing this. X is strictly greater, so to the right, of negative 3/5. So where's negative 3/5? That's like 0.6 or so that's like here. So negative 3/5. It's strict, so it's going to be an open dot. and it's to the right, because here x is greater than -3/5. But just like I did over here, right, I need to also graph my assumption. My assumption is that x is strictly less than -1/3. So -1/3 is like over here somewhere. So I guess I should have made this even bigger. And again, it's strictly less, so it's an open dot. And it's less than, so it goes to the left. So this is x less than -1/3. Again, you don't have to write these things along the lines. I'm just doing it so that you guys can see clearly which one should represent what. And just like over here, we need both of these things, so it's exactly where they overlap. So they overlap between -3/5 and -1/3, but they don't include either one because of the open circles. So my answer for this side is -3/5 to -1/3, and I use parentheses on both sides. Okay. Okay. Now the last step I'm going to do it over here so I can maybe do another example. So the last step is I have here the case and the solution I got, which I ultimately got down to here, ultimately got down to there. So I have this and this are both valid solutions. So here I said it's where they overlap because it's and, but it's because I need this to be true and this to be true. Since x could be either of these and it would still work, it's really this or this are both valid, right? X could be here or here, either way would be okay. And so I want both of these together, okay? So my final solution is the union of these two things. So it's -3/5 to -1/3, right? Open on both. Union -1/3 to 1. Now, technically speaking, there's nothing wrong with what I wrote there, but I wouldn't leave it like that, because if you think about what this means, I'm going from 1 up to -1/3 and including it, and then from -1/3 not including it to the left up to -3/5, meaning that really these are the same number, it's bridging the gap, right? So really this union is the same as just the interval -3/5 up to 1. And if you're not sure why that's the case, graph this and see what happens on the same piece, okay? So this then is my final solution set. And to do that, right, we had to take what was inside the absolute value, see where it was non-negative, so set it greater than or equal to 0, and then use that as my cases, right? Where is it greater than or equal to 0? Where is it not greater than or equal to 0? Meaning, where is it strictly less than 0? The whole inside. And it's possible that that this could actually be something complicated rather than just something sort of this straightforward. So let me do an example of that. Okay. In fact, I jotted one down to make sure I got one that was kind of interesting. So, same direction, find all x and r such that, in fact, let me do my question. So let's do x squared minus 1 plus 2. And that should be greater than or equal to x. Okay. So this is I want to find all real numbers x such that this holds, okay? So just like before, I'm going to start out by finding where this is true. Let me switch to a different color. So I'm going to take what's in the absolute value, x squared minus 1, and I want to know when is that greater than or equal to 0. Now your intuition might be to move the 1 over and square root. You can do something like that, but it's really easy to sort of mess that up because you have to be a little concerned about like if there's a negative versus a positive and whether you're flipping the the inequality depending on how exactly you're doing what you're doing, or if you need a plus or minus if you're doing it sort of the more traditional way. You can avoid all of those problems though by, instead of doing what I said with the add 1 and square root thing, instead factor this side. So x squared minus 1, that's a difference of squares. This is just x plus 1, x minus 1. So you have the product of two things, and you want to know when are they greater than or equal to 0. So basically what we're asking here is, when we multiply two things, when do we get a positive number or 0, right? We get 0 when it's 1 or negative 1. That's just the standard polynomial solve it when it's equal to 0 thing. And the only way it can be positive is if both of these things are positive or both of these things are negative, right? If we have a negative times a negative, we get a positive. If we get positive times a positive, we get a positive. But if they're off, right? If one's positive and one's negative, then we would get a negative. So you can do this by doing what we would call a sine chart. So just as a quick review, if you don't remember, so for a sine chart, you would graph where the zeros are. So I have 1 at negative 1, 1 at 1. Note I'm not putting in 0 because it's not a 0, right? That's usually where people get thrown off. And then you basically test anything that sort of is not these numbers in an interval, meaning like you test one thing between them, one thing to the right on that case, one thing to the left on the other one. And you just plug in a number and see what the sign ends up being. So if I want something to the right of 1, I could pick something like 2. I would get 3 times 1 is 3, and that's positive, right? Negative, I could pick negative 1,000, for example, which would be some big negative, some big negative. Negative times negative is positive. And for between, I could pick, say, 0, which would get me 1 and negative 1, which would get me a negative. Okay? However it is you go about it, the answer for this is that this thing is greater than or equal to 0 in the interval. So now I'm going to break up my cases. So I'm going to have case 1. So this thing is positive when either x is to the left of negative 1 or to the right of positive 1. So it's the interval, excuse me. Maybe I won't use interval notation because I didn't over there, so let me do the other one. So I have x is to the left, so less than or equal to negative 1, or x is greater than or equal to the right of positive 1. So it's in one of these two sections. And in that case, right, we said that the inside is not negative, so I can just replace it with the parentheses. So I'm going to get x squared minus 1 plus 2 greater than or equal to 2x. Okay. In contrast, my case 2 is going to be wherever it was strictly negative, which according to my sign chart is strictly between negative 1 and 1. So this is when negative 1 is strictly less than x, which is strictly less than positive 1. In that case, again, I know that the inside then is negative, so the sign gets flipped just like we did over here. So I'm going to have negative x squared minus 1 plus 2 greater than or equal to 2x. Okay. All right. So now that I have my two cases, I'm just going to solve them. So I'll just pick one of them, solve it first. So here I'm going to pick this one. So I'm going to have x squared minus 1 plus 2, so that's plus 1, greater than or equal to 2x. Here I can move the 2x over. So I have x squared minus 2x plus 1 greater than or equal to 0. And now I'm in a similar situation like I was over here, where my best bet again is to factor. So if I factor this, I will find that it is x minus 1 squared greater than or equal to 0. But hold on a second, because whatever x is, right, So it's somewhere in one of these intervals, but whatever it is, negative pi squared or something. Subtract 1, I still have a real number. It's some number. And then I take that number and square it. But squaring makes negative things positive and positive things positive. So whatever's in here, when I square it, I'm going to get a positive number, right? Or at worst, I'll get a 0, meaning that this is true for all real number, all real x. So if I'm looking at, I'm writing a solution set here, I'm going to have the 0, -1, +1, and then it's going to keep going. But if I'm putting on the top all of the x that's satisfied here, it's literally all x. This is what we would call a tautology, technically. So all x satisfied this thing. But remember, the easy to forget piece is that there's something else, right? There's also this. So although this solution works for all x, I still need to account for the assumption. Right? So my final sort of solution on this side is where these overlap, which is exactly my assumption. So it is x less than or equal to -1, or x greater than or equal to +1, or if you'd rather the interval, -infinity to -1 close, union, closed 1 to +infinity. Okay? So that's this side. And this is a tricky observation, right? Because it's sort of weird to think that my answer is all numbers, but it really can happen. So then over here with case 2, I'm going to essentially approach it the same way. So I'm going to have negative x squared plus 1 plus 2, so that's plus 3, greater than or equal to 2x. And now, before I move the 2x over here, just because I like having a positive leading coefficient, I'm going to move it the other way. So I'm going to have 0 greater than or equal, so I'm going to add x squared over, plus 2x minus 3. And again, I'm in a similar situation, only here now I'm going to, so factor, I'm going to get, though, in this case, x plus 3, x minus 1. And again, I can do the same sort of sign chart argument, which I would encourage you to do. For the sake of sort of time in this case, I'm just going to sort of go ahead and say that this is true. So what this is saying is 0 needs to be greater than this thing, meaning I want to know when is this negative. And that's going to happen. So when is it non-positive, I should say, right? Because it can be equal to 0 as well. So it's going to happen between -3 and +1. Okay? But, so, well, I shouldn't say that yet. So I can do my solution set here. So let's do like 1 there, 0, -1, -2, -3. So this then is closed on both sides, and it goes from -3 to 1. So this is this interval, right? Which again, if you'd rather have it as an inequality, it would be -3 less than or equal to x less than or equal to 1. But again, right, remember we got to also include graphing our assumption, right, our requirement that x is strictly between -1 and 1. So wherever -1 is, wherever 1 is, these are open dots because it's, right, strictly less than. And so the total solution is where they overlap, which is exactly, again, the assumption. So it's going to be exactly -1 less than or equal to x, sorry, not less than or equal, just less than. less than x, less than 1, or open -1 to 1. Opened. And finally, sorry, I'm gonna squeeze it down in the corner here. Didn't use my board space exactly perfect. But I'm gonna have this and this as my solution set, right? So I'm gonna have negative infinity to -1, union 1 to infinity, union, so that was this piece, and then -1 to 1. But really this is everything but -1 to 1 and -1 to 1, right? So this is really just all real numbers, meaning that the actual solution to this problem is literally any number you want, any real number, you plug it in and it'll work. Which is not obvious, right? Because in some sense, like if I just chose a number like 1, I would get 1 minus 1 is 0 plus 2 greater than or equal to 2 times 1. So I get 2 greater than or equal to 2, which is true, as we would expect. But it's really close. It makes you think like if I picked something just slightly away from 1, would this thing get smaller faster than that thing and break it or something? And the answer is no. In fact, any number will work. Okay? So this is solving inequalities. If you were solving equalities, it is exactly the same process. The only difference is that you'll get an equal sign at some point, so your solution set, instead of being a ray or something, will just be a point, and then you would still take it where they overlap. So you get most likely a point instead of some set, which is why I stuck sort of with inequalities, because it's much sort of more elaborate how you would do them, but it's the exact same process. So you break it up based on cases, based on whether the inside is positive or not, which again can look kind of weird if you have some especially higher degree equation. And then you solve it and you sort of plot on these x number lines, I guess you would probably call them instead, not an x graph. So if you graph it on the number line, but then you also graph your requirement, right? Your respective assumption, and you take where they overlap. And once you've done that in both cases, you would take those two solution sets, merge them together, and if they line up nicely, because they don't always, they did in these cases, but they don't always, you would write them as sort of as dense a piece as you can to sort of simplify. Okay? So that is that.